Maybe some students don't know that I record all lectures and I post them on iLearn, just in case if you miss anything, just in case you want to listen to it again. So you have the chance to do that. So let's start with what I have done so far. What I have done so far, first of all, I told you we have three basic logic operations. The first one is not or inverter. The second one is and the third one is or. And using this basic operation, we are gonna build everything, logic circuits, okay, as you will see later, okay? So then after that, I started to explain, yeah, just I give you some idea here. How can I use this basic operation to make a function? For now, these functions are not doing anything, just for education. Later, this function can do something, okay? Addition, multiplication, whatever you want to do, as you will see later in this course, okay? But I just want to, what I want to see here, we can use this operation, the three main operation, to create something complicated or more complicated. We call it a function, okay? More importantly, and this is very, very important, is what we call a truth table. So truth table, actually, as you see here, it has input and the output is here. So this is a circuit. This circuit has two inputs, A and B. And I'm going to keep seeing it until, so as I told you before, every variable here is binary, 0 or 1, okay? It's not, can't be 5, 6, it's not a number, it's binary. These are 0 or 1, okay? Same thing here, this relation is gonna produce binary, also 0 or 1, okay? And then, as you see here, in the truth table, I put all possible cases, okay? So this all possible inputs, and then I calculate the output, okay? So this is the output of this function. So when this is the input, this is the output. When this is the input, this circuit is gonna produce this one, okay? Anyway, also here I'm expecting how can you draw a function. So if I give you a function, you should be able to give me a drawing like this one, or the opposite. If I give you a drawing like this one, you should be able to give me the function, okay? I give you more examples. Here I put a lot of examples. In the second part here, I started to explain basic or the main theorem or rules in Boolean algebra, okay? And I told you have to be careful here, because this is not, although there are some similarities with the algebra. We know the normal algebra, but also there are differences, okay? The main difference is, number one, in the normal algebra, if any variable can be a number, 7, 8, 10, 20, 1 billion, whatever. But here, every variable is just 0 or 1. Okay? Number two, we don't have, the operation we have here is different from what we had before. What we had before, addition, subtraction, multiplication, division. Here, we have the three main operations we explained, a logic and so on, okay? And then I started to explain some rules, okay? And then, so for example, if A or 0 is A, and then you can prove this one by logic, or you can prove all of them using a truth table. Look at what I'm saying? Truth table here, as you see here, for example, if I want to prove something like that, again, A is just one bit. A or 0 is A. So if you have here or, and then you have here 0, and here you have something, we call it A, so I'm gonna get A here, okay? And if you say this is a truth table, so this is A, I put all possible cases for A, and this is A or 0. If you look at the two columns, I can see the two columns are the same. That means they are equal. Anyway, so I explained other things here. Also, I talked last time about the duality. So duality means, okay, if I have a rule, something like that, if I have a theorem like this one, so this one is telling me this operation is commutative. So X or Y is equal to Y or X, okay? We have the same thing for sure in normal algebra, but this one is not or, this one is plus, okay? Anyway, so using this, if this rule is true, if this one is true, I can create another rule. We call it the dual, okay? So for every statement we have, I can make another one, we call it the dual. So if this one is true, this one is true. If this one is true, this one is true. So if the statement is true, the dual is true. You got what I'm saying? So this one is the dual of this one. This one is the dual of this one, or the opposite. So this one and this is the dual of it. To calculate the dual, as I told you here, all what you have to do, any or should be and. Okay. And also, that's what I'm saying here. Convert and to or. Any or, make it and. Any one, make it zero. Any zero, make it one. Anything else, don't change. So variables don't change. Variables, complement, don't change complement. Okay. So, and this is interesting because if we have 100 rules, I can make it only 50, right? Because the other 50 you can get it from the dual. Anyway, so I explained here several theorem related to Boolean algebra, okay? And the way we can prove any one of these, as I did here, the easy way to prove it is just a truth table, as you see here. So I want to prove this associative property, associative. So if you do x or x and y and z, it's the same if you do y and z first and then you do x. So it's the same. If you calculate this, I want to do x and y and the z. If I calculate this one first or calculate this one, it's the same. Okay. By the way, this is not something new. This is similar what you did in normal algebra, but just here the operation is different. For example, if you multiply 3 times 2 times 3 times 4, for example, it's the same. So if I calculate this one first and then multiply by 4, it's the same. If I calculate this one multiply by 3, it's the same. It's the same thing here. Okay. So can you prove it to me? Okay. If it is the same, why you have to prove it again? Because this is not multiplication. This is n. That is why you will see sometimes we have something here that is not in Boolean algebra. So you have to be careful here. It's not everything in Boolean algebra, it's going to be here, okay? Because it's a different operation. Anyway, so I want to prove it. The very easy way to prove it, I'm gonna calculate this way. Also, I'm gonna calculate it this way, okay? And then I'm gonna look at the truth table. Okay, this is truth table has all possible cases. And now I can say, and this is a very important thing, we're going to use it all the time. If I have to do expressions, how I can know these two expressions are equivalent or not, right? Equivalent means they give the same result. These are the same, right? But written in different way, but this is the same, okay? How I can know? The very easy way is just make a truth table and then look at this column here and look at this column. If these two columns are identical, so those two formulas are equivalent. Okay, that means for every input, both of them are going to give the same result. For any input, they are going to give the same result. If there is only one bit, only one entry or one bit is different, if one entry is different, they are not equal. What I'm saying? And this is something you can do in quizzes in exams. Listen to me. So in quizzes, if I ask you to use the truth table to prove this expression is equal to this expression, be smart. You don't need to calculate everything. Okay? Calculate as long as equal, continue. Equal, continue. Once you find one entry is not equal, don't continue. Okay? They are not equal. Now, there is no need to waste your time. Any questions? Then here I talked about the distribution. For this one, as I told you, this is exactly similar to the normal Boolean algebra. If you switch and by multiplication and or by plus, so you have the same thing in Boolean algebra. This one is not in Boolean algebra. Even myself, sometimes I forget this one. Okay? So what I did here, we did distribution, similar to this. So here you did distribution, A and B, and then A and C, and you keep this one. That's exactly what I did. Here is exactly same thing, but here we have or. So here, A or B, and then we have N, keep the N. Then A or C. Is that okay? So what I did here is exactly similar to what I did here. You have to keep the operation here and then do the distribution this way. Any questions? So here we have this one in Boolean algebra, but it is not in normal algebra. Anyway, again, I want to show you why this is true. The easy way to show you it is true to create the truth table as you see here, okay? See, in this case, we have 3 inputs. And I don't want to keep repeating, but I said it many times. The way you have to do it, I want to put here all possible cases. In order to make all possible cases, there is a pattern. The pattern is 0, 1, 0, 1, 0, 1, 2 zeros, 2 ones, 2 zeros, 2 ones, 4 zeros, 4 ones. Okay. One important thing, as I said before, how many entries you have here? Simply, how many variables I have? I have 3, so it has to be 2 to the power of 3. Okay. 2 to the power of n. That's what I told you before. For any n bits, how many different numbers I can have? Okay, this was a question in the quiz. Anyway, and then after that, I calculated this one here. I calculated this one here. Okay, and then I look, I find they are the same. That means it is true. Any questions? Okay, same thing for this one. I did it here. Also, last time I started to explain De Morgan theorem. Okay, so in De Morgan, as you see here, if you have X or Y, everything is inverted. So the inverter here is not for Y, it's for everything. Okay, again, remember, X is just 1 bit, Y is just 1 bit. The result of this operation also is just 1 bit. Okay, so anyway, so this one is equivalent to, look how it works. Okay, I'm gonna get inverter to the first term, as you see here. And then any OR, I'm gonna make it AND. This is OR, I'm gonna make it AND. Then I'm gonna get inverter for the second term. And any AND, I'm gonna make it OR. And this is the case here. So as you see here, we have here, I'm gonna get inverter for the first one here. And because the relation here is AND, I'm gonna make it OR, and then I'm gonna get the inversion for next one, okay? So this is what we call De Morgan, okay? Remember, this inversion for everything here, okay? And then again, I show using truth table why they are equal. So if you look at this one, they are the same. Using truth table, if you look at this one, they are equal. Just to prove, I want you to prove it, or I just want to convince you it is equal. But you can just use this. You can just use this theorem, okay? Any questions? Very important thing. Please listen to. Very important thing. Okay. Here, I give you example X plus Y inverter. Is that okay? However, in reality, this X can be a term, a complete term. Okay. For example, A, B, C. This Y can be a complete term, like A, B or C, a complete term. You got what I'm saying? Still, it can work. Please, okay. I give you some examples here to understand exactly what I'm saying. Okay. For example, here I want to get the inverter of this one. Okay. Can I use the same thing here? Wait a second, man. I can't use it because here you have X and Y, but here you have EB. You didn't tell me I can use it. Okay. It's very simple. If you are confused, very simple. I can call this one X. I can call this one, for example, Y. That's it. So you will find it still can work. Okay. Why you can call this one X? Simply because after you do this operation, the result is 0 or 1, right? So it's binary variable. So I can call it X. That's it. That's why you can see here, when I did the inversion, I just did the same thing. I do inversion for the first term. So here, what? Okay. Be careful here, guys. When I explain one rule, something like that, and you find something different here, your first thing is that, can I use this one here or not? Okay? Don't just use it because it may not work. You understand what I'm saying? Okay, I'm gonna clarify what I say. So here, this one, I was able to convince myself. Okay, simple. This one is similar to this one because I can call this one X and I can call this one Y, and then I can. So here, this is like X, and this is like Y. That's it, and then I can continue. Yeah, that's what I did. So what I did here, the first term here, the first term inverted, and then OR it becomes AND. The second term is inverted, and then I can apply De Morgan again. So here, this is one time. Now I can apply De Morgan again if you want. So same thing here. So you have A and B. So it's going to be A prime or B prime. Okay. Then here, C prime and then another prime. Remember when I told you C prime and then you add another prime, this inverter cancel each other. That's what happened. So here you have a prime here. So C prime and then you invert it again, you get C, right? Or D prime. Is that okay? Same thing here. I can simply you have two terms here. I can consider this one X. I can consider this one Y, and then I can use this one here. Very simple, right? So that's what I did. So I took the first term, I got the complement to the first term, and because this is AND, I'm gonna make it OR. Second term, I can get the complement. Now let's continue, okay? So inverter of inverter is gonna be C, okay? And also here, I can use De Morgan again here. Okay? So I'm gonna invert the first term, and then this is OR should become AND. And then you invert the second one. So this is the final result. Any questions? Okay. Look here. The idea of using a term instead of one variable should work for all the other rules I explained. But maybe some rules it may not work. But again, to make it easy for you, just see if you change this term and put it X, you're gonna get, because this is the correct form. Okay. Any other form, you have to make sure it's equivalent to this one before you use it. Otherwise, you can apply it for something and then it's not correct. You know what I'm saying? Let me give you one more example to understand exactly what I mean. So for example, here, I explained here, you have one variable or a term, as I told you, one variable, and then the relation is OR. What if you have case like this one, for example, here? It's not 2, it's a 3, it's not 2. Okay, can I use the other one directly? No, you have to think first, is that equivalent or not? Because I'm very precise. What I'm saying, if it is this way, it has to be this way. Is that okay? If it is different, okay, I can't say yes or no. But what I'm saying, don't just use it blindly without thinking. Don't do that, right? Because it may not work. And maybe you are gonna lucky and work. Just think about similar to what I did here. And that's what I'm gonna explain now. So what I'm saying here, this is not the origin, and maybe more. So for example, here you have X1 or X2 and so on. Okay, for example, it this way. Okay, think about it. Okay, first, and then again, I'm explaining this one here for De Morgan, but what I'm saying right now is valid for any other formula. Okay, so anyway, let's think about it. So very simple. What I can do is actually, as you see here, the result will be yes. It's the same like De Morgan. So if you have more than one, so I can do inversion for the first one, as you see here. Any OR, I flip it to AND and do inversion, flip it to AND. So this one is exactly equivalent to this one. But what I'm saying, you have to think why it is equivalent. That's what I'm going to say right now. So I can simply, okay, the original formula has only two, right? One X and Y. Okay, very simple. I can do the same thing. I can consider this one X, and I can consider this Y. Now I can use the other formula, the original one. Okay, so I can use it. Once you use it, so here X, this is X, okay, inverted, and X, Y inverted. It's gonna become here, okay? And then I can do De Morgan again for this one, okay? So if you do De Morgan again for this one, this is the result you will get. Okay, again, guys. So now you don't need. Okay, let me be very clear. Okay, for De Morgan, it is true if it is only two variable or more, it's gonna work, right? But please don't do that for any other formula until you make sure it is. If any other formats in the original one, you need first to make sure it's equivalent, right? I hope that as I told you, just X and Y. Okay, so you have to be careful here. Is the formula is saying we have only one or one. Is that okay? If anything else, you have to think is that equivalent or not? Don't just use it. Okay. Any questions? Okay, so we have one more theorem here. We call it absorption. So you can tell from the English name you are going to absorb something. So this one is telling us, as you see here, x or xy equal to x. Okay, so here you have some value here. It can be a term, and then we have the same value here, and then we have another variable here. Okay, so you have something here, and the same thing appeared here, and then we have y here. Okay, so actually here we can absorb y. Okay, so the result is going to be x. What is y? Where is y? Y has no impact on the result of the function. I can remove it. It has no impact. You got what I'm saying? Because the result always is going to be x. Okay. How I can prove this is correct? How I can prove this is correct? Again, there are two ways, not one. The first easy way is the truth table, as I have done before. The second way is you can use the rules I explained before, okay? You have to do algebra manipulation. So now we have algebra theorem. I can apply this theorem and see if it's going to give me. So there are two ways. Maybe this is a straightforward way, and there is another way using manipulation. So let's look at this one as well. How can you do manipulation? As I told you before, look what I did here. You know the distribution. This is the opposite of the distribution. If you have x, 1 plus y, I told you there is a distribution. You have to do this distribution. So it should become x or xy. Now I can do the opposite. X is common, a common factor. It's like a common factor, so I can take it outside. So x is here, x is here. So I can take x here, and after I take x, it becomes 1. Okay, so x and 1 is x, okay? or y, this one. Is that okay? The opposite of the distribution. Anyway, so this is algebra manipulation. Okay. So anyway, and then again, from one of the rules I explained before, one or y, one or anything is actually 1. Just if I go back here, you see this is one of the theorem I have here. And also I told you, we have here in the last slide here, I summarize all the theorem we have, and in quizzes, exam, something like that, I can bring this slide differently. Okay, but still, yes.
The variable matter.
One y plus yx equal 1 equal y. Yeah, it's exactly, man. This is exactly similar to this one. We have something here, I call it x. Someone can call it w, right? And then but this thing has to come here. So it has to be w, right? And then we have another thing here. I'm going to call it f. You understand what I'm saying? And this is kind of formula, can be a formula as well. For example, look here. For example, I have AB plus ABC. Look here, man. This is similar to this one. Wait a second. How it is similar? Very simple. This is x. This is x. And this is y. That's it. You got what I'm saying? Very simple. Anyway, so as you see here, what I did, I took x common, so it becomes 1 or y. And you know 1 or y is actually 1. And you know x and 1 is actually x. Got what I'm saying? How I know all of that? Yeah, because if you go back, what I explained, this is the rules we have here. Okay. A or 1 is 1. So all these rules I already explained here. So that's what we call algebra manipulation. So anyway, so this is, so if I have, I'm going to say it again, guys. Very simple. So what I'm saying here, if I want to prove this formula equal to this formula, or these two are equal, okay, how I can do that? I have two approaches, okay? You can use a truth table like this one, and then you have to calculate this one in the truth table, and then I have to compare it with x. I find it is identical. So that means they are the same, okay? This is one way. The other way, we can do algebra manipulation using the rules of algebra, okay? You know, this is again, this is not something new. You know, in normal algebra, when you had something like 3x plus 3 plus 7x plus something here, you can also apply some algebra manipulation to simplify it or to prove something equal to another thing. Anyway, so let's look at the second one here. This is the dual. So this is the dual of this one. So this one is actually the dual of this one. Okay. So can you see here? If I have something here, I'm going to call it X. It can be A, it can be F, something. It can be a formula, something. And the same thing here is repeated here. Or Y. So the result here is only X. Okay. Let's see how you made it. Okay. Again, you have the truth table here, and also I can do manipulation. So during manipulation, as you see here, number one, I can do distribution, X, as you see here. So X and X, or X and Y. Is that okay? And then here, X and X is actually X, or X and Y. So if you see this one now, it became similar to this one. And we already proved this one can go to X. Any questions? So again, similar to what you did in the normal algebra, number one, you have to understand the theorem. Number two, you have to use them. Okay. One more theorem here we have. We call it uniting theorem. Okay. So in uniting theorem, look how it works and try to understand it correctly. We have something, we call it X. It can be A, it can be B, it can be term, it can be formula, whatever it is. So we have something binary, 0 or 1, it's called X. And then multiplied by something else called Y. Okay. And then we have OR here. And then the same X is repeated. And the Y here is the inverter of this Y is Y is here. Okay. So we have something and something else. And then the same thing here in here. And the inverter of this, the second one comes. Okay. So if you have this one, the result is X. Man, wait a second. What do you mean by the result is X? Simply, I mean, Y does not have impact on the result. See? So even you have a circuit, so if you implement this circuit, you will find, yes, you input Y, whatever Y you put is not going to make a difference. Still, the result depends on your X. Right? So anyway, again, you can prove this one. This is the dual again. In the dual, as I told you before, every AND becomes AND. Or every OR becomes AND, as you see here. Okay. Inverter, you don't change. Variables, you don't change. This is the dual of it. Okay. So please prove it to me. Very simple. This is a very simple proof. Again, you can prove using the truth table, or you can prove using manipulation, algebra manipulation. So let's do algebra manipulation. Look here. Look at the point. Okay. X is here and X is here. So X is common factor. I can take it outside. This is the inverse of distribution. Okay. So that's what I did. So I took X outside. And this is a trick because you have Y and you have the inverse of Y. And the OR, as you know from what I explained before, this should give you 1. Y or the inversion of Y give you 1. Okay. And then X and 1 is actually X. Also, this is one from rules I explained before. Any questions? Okay. The second one here, I want to improve this one. So what I did, number one, I did distribution. So the way I did here distribution is so similar to the normal algebra, X and this one, and then X, this one, as you see here. Okay. Or Y with this one, and then Y with this one. This is how can similar. This is similar to normal algebra. So I just did distribution. After I did distribution, I find X and X. X and X is X. Okay, this is one of the rules we have. Y and Y prime. Y and Y prime is 0. Is that okay? Also, this one of the proofs one of the theorem I explained to you before. So now, and then I find here X has common here. There is X is common. Okay, so I can take X outside. And now 1 or Y prime, or if you have one, guys, if you have one or A, B, or C, or N, or F, or, it doesn't matter. The result is 1. Look at what I'm saying? Because if one input is 1, the result is 1 regardless of the other inputs. It doesn't matter. Look at what I'm saying? So that's why here we have 1 or y prime or y, and if you have more, it doesn't matter. Still, the result is 1 because this is how OR works. One input is 1. Don't care about the other ones. Okay. So now this one becomes 1, and then I got x at z. Any questions? Okay. So only 2 theorems are left. One here we call it elimination, and the other one here, this one. And then after that, I'm gonna move to the next section. So anyway, so let's start with this one, elimination theorem. Okay. Again, understand it very well. Number one, as you see here, you have something here, we call it x. Okay. And y prime or y. Again, you have something, we call it x. Okay? And something prime. Or this one is the same thing here. Okay? So this can be term, can be term, can be term. It doesn't matter. Okay? As long as this format. If it is this way, so actually here, the result is x or y. Okay. And this is the dual one. Okay, can you, again, I can prove it using truth table as I told you, or I can prove it, right, I'm gonna by using algebra manipulation. So let's see how can you do it here using algebra manipulation. So here comes the theorem sometimes I forget, okay? So if you have here x, y prime or y, is that okay? It's the same if I say it is y or xy prime. It's the same, right? Okay. And now I'm going to do the distribution. Okay. I do the distribution. So this one becomes equal to y or x and y or, okay. So we have or here, y or y prime. I do distribution. Okay. And now, yeah, as you see here. And now this term becomes 1. Y or y prime, it becomes 1. And I did the solution for that. I did the distribution in order to get this term, and this term is 1. And any term and 1, you get the same term. Any questions? You need also, you need to understand this mathematical manipulation, right? Why? Simply because for sure, this theorem you can just use. Okay, so you can just use this theorem. I'm not gonna ask you to prove a theorem, no. But if you understand the proof here, you will understand algebra manipulation. Because this is one thing for sure, 100% will be in exams with this. I'm gonna give you a formula, whatever the formula is, and I tell you proof this one is equal to this one. And in this case, you can, there are two, if I don't tell you how, it's up to you. You can use the truth table, which is much easier way for sure. Truth table is just put 1 0 1 0 and then do calculation. Yeah, they are equal. That's it. Much easier. But I'm expecting, or in this course, you should learn both of them, the two approaches. One approach using the truth table, the other approach is using mathematical manipulation. So although I'm not going to ask you to prove any theorem, still it's important to look at these proofs because this is like a practice. How if I give you any two formulas and I ask you to prove them using algebra manipulation, this can practice. Any questions here? The last one here, we call it consensus theorem. Look how it works. This is a little bit tricky, but once you understand it, it's just very easy. Look how it works. Look here. So we have here something, we call it x. Okay. And then we have here the inversion of x. So we have here something called x. Okay. And the inversion here. Okay. This multiplies by something called y and something called z here. And then we have another term, these two. Again, so I have here one variable and I have its inversion. And then I have these two. And these two actually here. Is that okay? Again, we have one variable and, okay, something we call it 1. And then the inversion, so I see a variable and the inversion. And then I see here, these two come here. In this case, if you see something like that, so this term here is redundant. I can remove it. Okay, that means this one is equivalent to this one. Any questions? Why? Yeah, for sure. Number one, I can make it using truth table. Okay. Also, I can make it using manipulation, algebra manipulation. So sometimes you have an extra term. This term, it has no impact on the result. It has no impact on the result. Okay? So if I remove this one, I get the same thing. So again, in exams, in anything, you don't need to prove this one to me. Just tell me I'm going to use a theorem. Is that okay? This is a theorem. You can just use it. But, and this is my main concern, you have to use it correctly. You have to understand it to be able to use it correctly. What do you mean? Very simple. It has to be this format, something, and this thing is inverted. This thing, it can be A, B, F, it can be term, whatever. Okay? And then you have here something N, something here N, and these two come here. If you have this exact format, you can just cancel this. You have to be careful here, guys, because you may, I'm sure, you may apply this rule for something for a different format, and then you are going to get wrong result. One more thing important here, guys. Although this is a theorem, but here we can understand a new concept I'm going to teach. We call it simplification. This is a theorem. Theorem means this one is equivalent to this one. So if you implement this circuit and then you implement this circuit, both of them are going to give exactly the same result. Okay. But this is related to something I'm going to explain. We'll call it simplification. Simplify. We simplify. Is that okay? So what this means? Which one is going to be more costly? This one is going to be more costly, right? Because we have here more terms than this one. This one needs more gates. You got what I'm saying? This one may need more time to do the calculation, more time. Okay. So this is a topic I'm going to explain shortly. Okay, in detail. So this section is about equivalent. How I can know if you have two things are equivalent. Okay, and already I explained it, but anyway, the second part here is about simplification. So simplification means look how this circuit and this circuit are equivalent. You got what I'm saying? So, but this one is going to be costly. I'm going to pay more money to do it because it needs more gates. This one I can use these gates. So two things here. This one is going to be more costly, and both of them are doing the same thing. But this simplified is not simplified. You got what I'm saying? So the word simplified means this number of terms, this number of gates, and both of them are doing the same thing. So any input here gives the same result. Is that okay? Not only about cost, it's also about time. Why? Because as you know, I think I put it, no, I didn't. As you know, here there is from the labs, we have propagation time here, propagation time. Okay. So it may not here in this circuit, because here you have two levels, and also here you have two levels. I may not save in time, but in general, simplification, number one, you can use less number of gates, can be cheaper. Number two, also, for example, if you have something like that, okay, a circuit like this one, for just an example, I have two levels. So how much time is going to take? There is a propagation time here and another propagation time here. So in total, if you have input, in order to get the output here, I have to add this time to this time, propagation time. Is that okay? If I have another one, it's actually three levels or four levels. Okay. Something, whatever it is. Okay. So something like that, for example, just anything. Okay. And I tell you, these two are equivalent. Okay. For sure, this one is much better. Why? Because here we have two propagation time, but here, look here, 1, 2, 3, 4, right? So this one is going to take more time. So what I want to say, simplification is not only important. I can do the same thing using small number of gates. No, it's not only that, but also it can be fast circuit. Okay. because there is a propagation time. Yeah, you have a question here? Yeah, so you have a question here?
Oh, no, you answered it.
Okay. So, yeah, let's come to this one. So also I'm gonna explain here the proof, not because in exams, I'm gonna ask you to prove the theorem. No, I'm not gonna do that. This is theorem, so you can just use. But from the proof, you can learn how can you apply or how can you do algebra manipulation so that when I give you something else, you can do it, okay? So let's see, again, you can prove using truth table or you can prove it using algebra manipulation. So let's start with the algebra. Let's do the algebra manipulation right now. So first of all, I'm gonna do a trick here, and this trick is gonna help me. Look here, this one here, I'm not gonna change the first two terms, but I'm gonna change only the last term. Okay, x or x prime is 1. So actually, I didn't do anything. I just, this is y and z and 1. It's gonna be y and z. I didn't do anything. What I'm saying? But here, so I put this term and I know this term is 1. So it has no impact. Okay, but why I put it this way? Because it's gonna help me the next step. Anyway, for sure, this is, I know this is difficult. So I'm not in exam or anything. I'm not gonna give you something complicated like this one, because this is not like systematic. Systematic like truth table. Truth table, you know, put 1 0 1 0. Look at the result. This one needs some kind of thinking and more difficult. But for sure, you need to know the theorem, and you need to know when you apply the theorem to prove or to do algebra. Boolean manipulations. Okay, so once I did this one, okay, then here I'm gonna do distribution. So now I got this term from here, and then I got this term from here. Is that okay? This is the difficult part. After that, everything is very easy, very simple. Look at the trick I did. I noticed I have here xy is common here. I'm telling you a tricks. How can you think about it? Because yes, algebra manipulation is easy, right? So I see something common here. So I can take this one common. So these two, I can make it xy and then 1 plus z. Is that okay? Because something common. Same thing here, I can see x prime z is common here. So I can take these two terms together. I put x prime z, and then I will find 1 plus y. And 1 plus 1 is 1. So it has no impact, it's just 1. This one also has no impact, it's 1. So this is the result I got. Again, the tricky part or the difficult part is the first step. But once you do the first step, the next one should be easy because I find this part is common. So I can take it common here. Once I take common, I got rid of z. Right? That's 1 or z is 1. Any questions? Okay. So this is the summary of what I explained, the theorem. So now, so again, let me tell you. I explained many Boolean algebra theorem here. Okay, number 1. So someone can ask me, okay, how I can use it? I already answered the question, but I want to repeat it. Okay, how we are gonna use it? Okay, you are gonna use it for one of two things. If I give you two functions and you want to see if these two functions are equal or not. Okay, as I explained, one way to do it, and this is actually the topic of this next section here. Next section is about equivalent and simplification. Also, we can use the theorem in simplification as well. Okay, so, and you know what I mean by simplification? Simplification means I can make a circuit. This is doing something, and this is a side to the circuit. Someone else can come with a small circuit and do the same thing. The small one is better. Why? It's cheaper. You don't need too many gates. Number 2, faster, right? So that's why it's better. So here's that's what we call it about simplification. So equivalent, that's a topic I explained. If you have two formulas, for example, I have these two formulas, and I want to prove that these two formulas are equivalent. Okay. Again, as I explained in exams, in anything, there are two ways. If I don't tell you in quizzes, in exam, in anything, if I don't tell you what approach you have to use, it's up to you. But now you have two approaches. Either use truth table and either use algebra manipulation. I'm going to show And this is similar to what I explained before, nothing is new. So if I want to do here, using the truth table, number one, you have, because I have here 3 variables, A, B, C, so I have to put all possible cases for A, B, C, okay? And then I have to calculate this term, and then I have to calculate this term, and then I have to compare them to cases. Once I did, look here, compare bit by bit, this similar, they are equal. Only one is different, they're not very similar. Okay. So, however, in order to calculate this term, I have to get AB prime. AB prime. But in order to calculate AB prime, I have to get B prime first. Okay. That's why I make here this is B and this is B prime. In B prime, I just flip all the bits here. Just flip them. Okay. AB prime, I actually did N between B prime and A. I got this. And then after that, I'm gonna take this column, and then I OR this column with this column here, sorry, this one with C. And this is the result I got. It's the same thing for the other term. In order to calculate this term, I have to get A or C. That's what I get here. Okay, we have A and C, I did OR. And then B prime or C, I did it here, okay? And then I do AND. Then I compare both of them together. Any questions? This is using truth table. Yes.
So on a quiz or a test,
yes.
Do we need to end it?
In exams, in anything, I can. This is the question, exact question. I'm gonna ask you. Proof. This one is equal to this one. Okay. If I say it this way and I don't say how, you can do it in 2 different ways. Either this one or that one. Or sometimes I can be very specific. I can tell you using full algebra manipulation or using truth table. Right, you need to learn both of them. Yes.
We use, say, use the truth table. Do we need that's the highlight.
Okay, my advice to you to avoid making mistakes, you have to do the for me, if grading, I may not care about this one, but I think it's better for you to do them. Otherwise, it's gonna be because this is a difficult part. You only make one mistake here, everything is wrong. That's why my advice to you, try to do it, because this is gonna make it easy for you to calculate this one and this one. Okay. So let's look at this one here. It's the same question. If I want to prove it using Boolean algebra, so what you can do here, guys, is I can take this one and I make it equal to this one, or it's the opposite. You can take this one and make it equal to this one. That you have to start from one side. It doesn't matter if you start from here and make it equal to this one, or you start this one and after manipulation equal to this one. It doesn't matter. So what I did here, guys, I just, for some reason, when you go home, you can try the other approach. But anyway, for some reason, I started from here. Okay. So here, first I did distribution. So this is distribution this way. I took this one, did distribution. Okay. So I got this one. And now the first thing I can notice, this is C and C. C and C is C. A and A is A. B and B is B. Okay. F and F is F. Right? This is N. Okay. So C and C is C. Okay. This is number one. Number two, again, I can notice there is a common factor here. Very important thing to look at the common factors here, because there is a common factor, so I can take C is common. The opposite of distribution. So I can see C common. Once I have C common, I actually canceled all of this. Why? Because you have one here. One or anything is one. Okay? And then C and one is C. That's it. Any questions? Okay. Yeah, this is just another example. I'm not going to explain it. When you go home, you can check it. But in this example, again, I give you 2 functions. This way, I ask you if they are equivalent or not. So here, because in every slide I show you and they are equivalent. So you doesn't mean everything is equivalent, right? So I just want to give you an opposite example. Okay, so here I did here X, Y, and Z, and then I can put F1 and F2, F1 and F2. And then when I look at the output here, I find it's not equivalent. Again, in exams and quizzes, you don't need to waste your time. Okay? Once you find this one here is not equivalent, don't complete. Okay? Because it's got to find only one entry or one case that's not equivalent. Any questions? Okay. So the second thing I'm going to explain is how can you use the theorem? How can you use the theorem I explained before? It's not to prove something is equal to something. No, to simplify. Okay, to simplify. And yeah, for example, I can show you if you have here, if you have this one, okay, and this one is actually equivalent to this circuit. Okay, this one is actually equivalent to this circuit here, this one, or equivalent to this expression or function. Okay, this one. That means they are the same. They give you the same result. But as I told you, this one is going to be cheaper, so it's better always to have to simplify the expression. Okay, always we do that. So to do simplification, we are going to use one of two approaches to do this simplification. Again, the theorem I explained, usually you are going to use it in one of two things: to prove expression is equivalent or equal to another expression, or to simplify, okay, and a function. So in simplification, we are going to use algebra manipulation. Okay. Also, in next chapter 3, we are going to use something like more systematic, like something like truth table, more systematic, because I know algebra manipulation sometimes is tricky, sometimes it's not. That's why, for sure, I'm going to bring a question here in quizzes exam. I'm going to ask. You need to learn how to do algebra, but I'm not going to make it too difficult, right? Because sometimes it's tricky, but you need to know. Okay? And the second approach, and both of them give the same result, is called K-maps. And this will be the topic of chapter 3. Okay? So again, if you want to do simplification, you can use algebra manipulation, and that's what we're doing in this chapter. In next chapter, I'm going to use K-maps. So I hope you understand what I mean by simplification. Okay, two functions, they do the same thing, but shorter. Shorter is better, right? So, okay, what is the benefit of doing simplification? How in this section I talk about algebra manipulation. In next one here, we're going to talk about K-maps. Is that okay? Before I continue here, I want to just jump this part to go to next section. I will come back here. Nothing here is new, but I will come back to explain how, for example, how from this one here to how I was able to simplify this one using algebra manipulation. You have a lot of examples because I know simplification is somehow tricky. Sometimes need somehow to think about it. You may forget one rule. So for example, from this one, I was able to simplify it all the way to this one. So I'm gonna come to this section again, but I wanna jump it. I wanna move to the next one because we need this one in labs. Okay, so that's why I'm gonna do this one first, and then I go back. So so here, as I told you guys, I explained the 3 main gates. Until now, I explained 3 main gates. I explained AND, I explained OR, I explained inverter. I explained the 3 main gates. In this section, I'm gonna explain 4 more gates. Okay, these 4 main gates are created because these are the basics ones. So these 4 gates are created from these 3, but I'm gonna use it as a gate, as a symbol, as a unit. But inside this unit, you can find these symbols, this basic ones. Okay. So here I want to explain what we call NAND, NOR. These are 2 gates. The other ones here, exclusive OR, exclusive NOR. So let me explain. Number 1, what is the symbol? How they work? How can you use the basic operation to create these ones? I'm going to tell you now. So let's start with NAND. NAND is actually, look here. This is first, what is the symbol? This is the symbol here. Oh, wait a second. This symbol is exactly similar to AND, right? So this is A, B, and Y, but you put a bubble here. Yes, just true. Okay. So this is AND. Without the bubble, it's AND. This bubble, okay, it is NAND. And actually, NAND and NAND is actually twin. So there is a small difference between them. The small difference is it just. By the way, I'm sorry, I'm going to correct this one. I got this one from the internet, but it seems to me everything I okay. because this one shouldn't be here. Okay, I just got this picture from the internet. Because so actually, so please remove this one. I'm gonna correct it. Okay, so actually, this name is actually N, and this one for inverter. This bubble means inverter. So actually, this one is equivalent to doing N, and then I'm gonna invert the result of N. Okay, guys. So this one is exactly equivalent to this one. Okay, so and after the end you put inverter here. That's why the relation here y should equal a and b inverted. Everything is inverted because this is n followed by inverter. Is that okay, guys? This is a symbol here. How it works is it's gonna work same thing like n, but I'm gonna invert the result of n. So if you look here, this is the inverted result of n. If you remember, I told you how n works. The only way to get one from n when all inputs are ones. One give you one. Anything else is zero. Now I'm gonna say just this one, I'm gonna make it zero. The only way to get a zero, which is the inverted of one, when the two inputs are ones. Anything else is one. Anyway, so it's not something new. Just I build on what I explained to you before. Again, the only way to get zero here is actually when the two inputs are one. Why? Because when the two inputs are one, and it's gonna give me one, inverter make it zero. Anything else, and it's gonna give you zero, then it's gonna make it one. Makes sense? So it's think it this way. It's not something new. It's the same thing I accepted for n, but I inverted the result. That's it. Okay. So can you have more than one input? The answer is yes. You can have more than one input. How it works is exactly the same thing. The only way to get zero here, this is the symbol. Okay. The only way to get zero here when actually all inputs are one. Because and is going to give me one, inverter make it zero. Anything else, you get zero. In other words, if one input is zero, I'm going to get one. At least one input, zero, I'm going to get one. I don't want to confuse you, but because in and, if one input is zero, I get zero. Here I get one. Just invert it to the output. It's not difficult. Okay. So this is the result here. Any question? So this you call it NAND. Okay. So we're going to use this symbol as a gate. Okay. We have another one, we call it NOR. Same thing. I'm going to use the same thing again, but here, NOR, again, I'm sorry, I just got this one from the internet, but it seems to me not everything in the internet I should trust. Anyway, so actually the way it works is here, there is no inverter here, okay? So actually here is, oh, I'm sorry, this is completely wrong. So I'm going to correct it. Look here. I'm going to collect this one. Now I'm going to collect it in the slide. So this one actually is OR. So this one, A or B, okay, is OR, and then inverter after this one, A or B, inverted. Okay. So again, NOR, similar to NAND. But the difference is I'm going to use now OR instead of AND. Right? So now this one, this is the symbol here. This is the symbol you can see here. This is the symbol for OR. This is the symbol for OR, and this bubble here means not. Okay, and that's exactly how it is. So this one is actually internal. This one inside this one it is OR, and then we have inverter here this way. Okay, so again I'm gonna correct this one. So how it works again? It's the same thing like OR, but I'm gonna invert the result. Right, same thing like OR. Remember how OR works. In OR, I told you the only way to get a zero when the two inputs are zero. Is that okay? Now I'm going to say in NOR, the only way to get one is actually when the two inputs are zeros. Okay? Yes?
So is a NOR gate faster than OR gate and a NOT gate?
No, I can't say. It depends on the technology you are using. So here it's related to electronics. But maybe I'm going to answer your question later. So if we can do everything using AND or not, so why you have these new gates? Is that okay? I'm gonna, because sometimes in electronics it's easier and less expensive to design NOR gate or NAND gate than designing OR and AND. Also, as I'm going to tell you right now, okay, we agree on something. The basic three operation we need: AND, OR, inverter. These are the three basic operations. Okay. Even when I introduce a new gate, it came from this one. Okay. Also, there is a reason, and also that's what I'm going to do in the coming lab as well. And that's what I'm going to explain as well. Using AND or NOR, sorry, NAND or NOR, you can actually do AND or inverter as well. So what you mean? I mean, if I have a good electronic circuit for NAND, I can actually make everything from it. From NAND, I can make AND, I can make OR, I can make inverter. You get what I'm saying? So that's why it's interesting this way. So as you will see. Okay. Anyway. So here, see, this is how it works here, as I told you guys. When the only way to get a 1, when actually the two inputs are zeros. Why? So you can see this is the inverted of the truth table of OR. Because if the two inputs are 0, OR is going to give me 0. Inverter will give 1. Same thing, I can have more than one input. It can be 3, 4, 5, 10, and so on. Because some students are confused. When I give example for 3 input, you may think it's always 3 inputs. I give example for 2 inputs, it's always 2. No, it can be 1 million inputs. You got what I'm saying? Because this is a logic operation. Anyway, so here, if I have here 3 inputs this way, so this is the result. You end the input, so it's actually similar to you have AND, and then you have inverter after the AND. And usually when you see this bubble means inverter. When you see, sorry, when you see this bubble here, anywhere, so this bubble means inverting anyway. So how this one work? Very simple. The only way to get 0 here is actually when the 3 inputs are zeros. This is the only way, right? And that means the only way I get 1 here when the 3 inputs are zeros. Anything else is 0. Any questions? Good. Now I want to move to the 2 more gates, other 2 gates. One is called exclusive OR, and the other one is called exclusive NOR. So let's see the number 1, symbol and how it works. The symbol and again, these 2 are gonna come from the basic operations I explained to you, the basic gates, as you will see right now. Okay, but let's see. First of all, this is a symbol. We use this symbol for exclusive OR. And we use this symbol for exclusive NOR. By the way, correct this one. In your slide, correct this one. I think this one was, which for sure doesn't make sense. It can't be the same operation here. So, okay. So you can, so let's start with one by one, okay? I don't want to confuse you. So let's start with exclusive OR. So here, this means X, look here, this is the symbol, X exclusive OR Y, okay? How it works? First of all, what is the symbol? This is the symbol. So the symbol, this means exclusive OR. So symbol is similar to OR, but I put something here. You got what I'm saying? So similar to OR, but I put something. So this is exclusive OR. How this exclusive OR works? What is the truth table? Okay, we call it exclusive OR. Exclusive OR work is this way, as you see here. I'm gonna say it in 2 different ways. Hopefully you understand well what I'm saying. I can say this truth table in 2 different ways. Number 1, look here. When the 2 inputs are equal, 0, 0 or 1, 1. So this one is gonna give you 0. When the 2 inputs are different, you are gonna get 1 and 1. You are gonna get 1. So this one is gonna measure if the 2 inputs are equal or not. But this one is gonna give you 0 when they are equal, 1, 1 or 0, 0. Okay? It's gonna give you 1 when they are not equal. Is that okay? This is how it works. I'm gonna explain it also in another way. Both of them are important. The 2 ways I'm explaining it, it's important. Look here, if I have exclusive OR, I have here 1 and the X, you are gonna get X prime. If you have exclusive OR, you have 0 and X. Okay, you are gonna get X. Okay, man, can you show me how you come up with these things? I'm gonna say, look, I'm gonna show you. Look here. When the input is 0, based on what I said here, when the input is 0, the output is equivalent to the other input, right? And this is exactly what happened here. The input is 0, right? Input 0 got 0, input 1 got 1. So when input is 0, the output should equal to the other input. That's when the input is 1, so I'm gonna get the inversion of this one. And this is exactly you can see. When one input is 1, right? With 0, I got 1. 1, I got 0. Any questions? So exclusive OR can tell you if you give you 0, that means the two inputs are equal. If it gives you 1, that means the two inputs are not equal. Is that okay? Again, as I told you, this one should come number 1 for this new gates. Number 1, you need to know the symbol, this symbol, and also you need to know this symbol. You need to know how it works, the truth table. Also, as I told you, we are gonna build everything from the basic three operations. So tell me what is the operation of this one? Pretty simple. So this operation is, so this is the operation of this one. Okay. So xy prime or x prime y. So this is exclusive OR. Is that okay? Can you give me a hint how it works? I'm gonna tell you how. Look here. If you look here, x and the inversion of y and the inversion of x. Okay. I want this one if they are equal. Look here, or if they are not equal, one not equal, I want to get 1, right? So not equal means, for example, this one is 0, x is 0, y, for example, is 1, right? So if they are not equal, like this case, for example, I am sure one of these terms is going to give me 1, and then I'm going to get 1. Why? Because I'm going to multiply 1 by the inversion of the second. So this is 1, and this is 0. 0 is going to become 1, and this term is going to give me 1. Okay, by logic. So by logic here, I designed it so that, okay, so that if you, if the two inputs are different, okay, so I'm going to take 1, and the other one I'm going to invert it so that this term is going to give me 1, right? And if they are the same, you are going to get 0. So this is actually the equivalent one for exclusive OR. Okay, guys. Usually in the future, we're not gonna use this one. But I'm gonna consider we have a new gate, right? New gate, exclusive OR, and just use it, right? Forget the details. We have exclusive OR. You should know how it works. We have named. You should know how it works. We have NOR. You should know how it works. Any questions? Okay, now we have another one, which is a very small variation. So what I did here, as you see, it's called NOR, exclusive NOR. So exclusive NOR is actually exclusive OR, and then I put inverter. Okay, even the symbol is the same, I just put inverter. Okay, I just put inverter here. So these two are exactly same thing, but just I put inverter here. That's why if you look here, yeah. So here, exclusive NOR, well, this is the symbol for exclusive NOR, is this one, and then there's a dot here. It's actually exclusive exclusive OR, okay, inverted. That's why I asked you to correct this one here. This was a typo. I'm gonna, so this one actually it was some exclusive NOR, which is not consistent with this one. Okay. Anyway, again, I just converted the output and created a new one. It's called exclusive NOR. How it works? Look, it's the same thing. Look here, I told you, if they are the same, I'm gonna get 0. Right? If they're the same. Here, if they are the same, I'm gonna get 1. Makes sense because you just invert. It's almost the same, right? So if they are the same, you're gonna get here 0, I got 1 here. If they are different, here I get 1, here I get 0. Okay? So this gates can be used if you want to measure if they are equal or not, because it can tell you if they are equal. Any questions? And then here, yeah, just I'm gonna leave this one to you, okay? This is a mathematical proof. So here, if you have inversion here, you can invert this one. So if you go all the way until the end, you can find this is actually the equivalent for this one. So exclusive NOR, I can create it using this one, okay? I did manipulation, just De Morgan, and then I just make simplification this way, okay? I think I explained this one. When you have 0 exclusive OR of X, you get X. 1 exclusive OR of X, you get X prime. X exclusive OR of X, you get 0. Why? Because the two inputs are equal, X and X. The two inputs are equal, right? So I get 0. Here, X and X prime, so I'm sure the two inputs are different. You get 1. This is a theorem. Be careful. The theorem I explained to you before don't work here. Be careful, please. What I explained to you before, it was for AND, okay, or inverter. Okay, that's what I explained to you before. The theorem I explained to you before. Okay, if you want to apply any one of them, you need to check if it works or not. Okay, I didn't say the theorem I explained to you before should work for XOR, because since it's a different operation. Anyway, but here you can also it's a commutative. Also, it's associative. So if I calculate this XOR first, and then I do this XOR, it's the same if I calculate this XOR, this one and this one this way. Also, we have distribution works here. The distribution works. So I can do here, this is the relation is AND. So I can do AND here and this one. This one works, right? Be careful here. It's not everything I explained before can work here. Okay, what if, so you explain to us, if you have 2 inputs, what if you have 3 inputs? How it looks like? Yes, you can have 3 inputs. It's gonna look something like that, as you see here. And actually, the way you can calculate the truth table is actually something like that. So you calculate, you know what this means? So you can calculate the XOR for these 2, and then the result XOR with the next one. Okay. So here, XOR, you XOR these 2, and the result, so it's gonna look something like that. The logic here may be different from what I explained before. Here it's not about equal or something like that, because it's 3 gates. It's different. It's a different case. You understand what I'm saying? You can see you have a different truth table here. But you can see, I'm saying here, if you have 3 inputs, so this one is actually equivalent to you here. You do XOR and then another XOR. These are all the logic circuits I explained. We have AND. These are the basic ones. And then you have NAND. This is just a summary for NAND. We have here NOR, we have XOR, we have XNOR. Okay. Any questions? Okay. We still have 2 minutes, so I can explain here also something here. I told you, as I just told you, the good thing about NAND, if we can do everything using AND, OR, and inverter. So why we need NAND? I told you because using NAND, I can implement any circuit only using NAND. So if I have a nice electronic circuit for NAND can be used to do AND, to do OR, to do inverter. So if I have nice electronic circuit NAND, I can use it to implement everything. So all the circuit is going to be only NAND. Same thing for NOR. How? Tell me how. That's what I'm explaining to you here. Look at this one. If you have NAND and you tie the 2 inputs together, it becomes NOR gate. If you have NAND and then I put this one next to it, I make AND gate. If you want to make OR gate, it has to be this way. So I have A prime, B prime. This is A prime, right? Because this is inverter. You can see this is inverter using NAND, another inverter. So A prime, B prime. So if you look at the result here, A prime, B prime inverted, because this is NAND. So if I have an NAND and I input here A prime, B prime, this one is equivalent to A or B. Are you sure? Yes. If you don't believe me, you can do very simple. You can do either truth table or simple manipulation. I'm gonna do simple manipulation right now. Look here at this one. And what I'm telling you, A prime, B prime inverter. Just De Morgan. So De Morgan is gonna tell me A prime prime or B prime prime, which equal A or B. That's it. So as a conclusion, using NAND, I can do everything here. Same thing, just give me 1 second to finish this slide. Same thing for NOR. So for NOR, also I can do everything using NOR. That's why we love them. Because if you have a nice circuit for NOR, I can implement a whole circuit, for logic circuit from NOR. Okay. So here I can, this is a NOT gate using NOR, and this is actually OR gate, and I can create AND gate this way using NOR. Okay. Again, how can you, are you sure this give you, this is A prime, B prime? So this should be A prime or B prime. Everything is inverted. So this one should equal to A and B using De Morgan. Any questions? Yes. F here is the output or a function F. Just a variable F. Okay. It's like an equation when you say y equal to x plus 1 over x2 whatever. So this is the result, the variable. Okay. And this variable is 0 or 1.